We all use GPS every day to get us to the right street, and it's pretty good. But what if pretty good isn't good enough? What if you needed to know your position not just on the right street, but on the right centimeter? Well, today, we're going to crack open the incredible precision puzzle that makes that happen. Okay, so let's just dive right in. The big question, really, is how in the world do we make that massive leap in precision? I mean, how do we go from knowing we're somewhere on the sidewalk to knowing exactly which paving stone we're standing on? The answer, it turns out, is a brilliant technique called RTK. And the difference is just staggering. Your standard GPS, like the one in your phone, gets you within about a meter or so, 3 feet. But with a technique called RTK, that's real-time kinematics, we're suddenly talking about 1 centimeter. That's 100 times more accurate, and it is the key that unlocks everything from self-driving tractors to mind-blowing drone maps. So how is this even possible? Well, the secret isn't some single, super-powered GPS receiver. Nope. The real magic of RTK is all about teamwork. It's a clever setup using 2 receivers that work together to hunt down and just eliminate errors. So the setup has 2 main players. First, you've got a stationary base station. This is just a GPS receiver that's been placed at a location we know with extreme, almost perfect precision. Then you have the rover. That's the receiver on the move. It could be on a surveyor's pole or an autonomous tractor or a drone. And because they're relatively close to each other, say within 10 to 20 kilometers, they're looking at the same satellites and dealing with the same atmospheric distortions. So the base station, knowing its true position, can figure out the error in the signals it's getting, and then, in real time, zap that correction data over to the rover. But here's where it gets really interesting. Just correcting for those atmospheric errors, that's not quite enough to get us down to the centimeter level. The real secret, the key to the whole thing, lies in solving this clever little puzzle that has to do with the very nature of the GPS signal itself. And that puzzle has a fancy name, carrier phase ambiguity. Now that sounds super technical, but stick with me. GPS satellites send out signals on a carrier wave. We can measure the phase, think of it as a tiny fraction, of that wave with incredible precision. But, and this is the big but, we don't know the exact number of full waves between the satellite and us when we start listening. It's an unknown whole number. This analogy explains it perfectly. Imagine you have a really, really long measuring tape, but it has no numbers on it, no inch or centimeter marks. You can see the tiny little tick marks between the inches perfectly, so you can measure fractions with amazing accuracy. But you have no idea if you're starting at the 5-inch mark or the 105-inch mark. To get the true distance, you absolutely have to figure out that starting number. So this is the fundamental trade-off we're dealing with. Standard GPS uses what's called a code measurement. It's unambiguous, it gives you a direct distance, but it's only approximate. The carrier measurement, on the other hand, is ridiculously precise, down to millimeters, but it has that ambiguity problem we just talked about. So the entire goal of RTK is to get the best of both worlds, to use the rough code measurement to help solve the puzzle of the super precise carrier measurement. So how does the system actually solve this puzzle? It's not like flipping a switch. It doesn't happen all at once. The process actually unfolds in 2 really distinct stages. It starts with a very, very good guess, and then it zeroes in on that final ultra-precise answer. The first stage is called RTK float. In this phase, the system is using some really complex math to come up with an initial solution. It calculates those unknown numbers of wavelengths, but as decimal numbers, like 100.3 or 50.7. Not the perfect whole numbers that we need. It's a really accurate estimate, but it's not the final answer yet. We're getting warm. And then comes the magic moment, the second stage, RTK fixed. This is it. The system successfully resolves those decimal ambiguities into their correct whole numbers, or integers. The puzzle is solved. This fixes the solution, and that's when the position accuracy just snaps into place at the centimeter level. And just to put some numbers on it for you, in that float state, you're looking at an accuracy of around 10 to 50 centimeters, which, hey, is already way better than standard GPS, but it's not the goal. But once the system achieves a fixed solution, look at that jump. We're now down to 1 to 2 centimeters of error. That is the incredible power of correctly solving for those integers. It's a total game changer. So how does a receiver actually make that incredible leap from float to fixed? Well, it's not just random guessing. It follows a really clever 3-step mathematical process to lock in the correct answer. Okay, so first, like we've seen, this system gets that initial float solution with all its decimal numbers. Then comes the hardest part, the search. The receiver's little brain runs this sophisticated algorithm. It's basically a statistical process of elimination. It tests tons of different sets of whole numbers, looking for the one combination that best fits all the satellite data it's seeing. Once it finds a set that it's really, really confident in, it locks it in, and bam, step 3. It applies those correct integers to the data to calculate that final, rock-solid, fixed position. And I want to stress that step 2, the search for the right integers, is incredibly complex. As this quote from Nevipedia points out, you can't just try every single possible combination. That's a brute force approach, and it would just take way too long. This is where decades of research have gone into creating these super efficient algorithms that can solve this crazy puzzle in just a few seconds. All right, so we've been diving deep into some complex math to solve this puzzle. But why does any of this matter? What does this jump from a float to a fixed solution actually let us do out there in the real world? Well, this level of precision is absolutely revolutionary. For surveyors, it means mapping land with pinpoint accuracy in a fraction of the time. In agriculture, it lets tractors plant seeds and spray fertilizer in the exact same furrow year after year, saving tons of resources. It guides giant construction equipment, it lets drones create perfect 3D models, and yeah, it's a key technology for the whole future of autonomous vehicles. And all of that is because we found a way to solve that clever little integer puzzle. It really leaves us with this final, exciting question. Now that we can pinpoint our location on Earth to within the width of a thumb, what are we going to build with that power next?